it should let me hit that. There we go, and it should let me. Why won't it let me go full screen? Come on. I don't know. I'll try in a little bit. Anyway, so you should have subtracted the 4, divided by 2, and squared it, right? Added the 1, divided by 2, and squared it. Sine squared plus cosine squared equals 1. This is the format this one should be in. The oops, God dang it. I'm going to have issues today. I can tell already. Ah, barnacles. Anyway, you should have written that one and multiplied by 4 on the other side, because when it's circular, it'd be like x squared plus y squared equals r squared. So make sure you didn't leave that 4 in the denominator. You leave them when they're different, because that's standard form for an ellipse, right? But when they're the same, whip it over to the other side. So I just have to reload my notes for today. I'm actually gonna, all right. It's the first thing that's in their ear. All right, so anyway, when you're doing the derivative, it gives you the same information you're used to giving you. So I want you to circle this just so you know. It doesn't give you any different information. It's just a different model. Because you don't have y as a function of x, you have x as a function of t and y as a function of t. So when we do dy dx, it's still the first derivative. It still gives you the slope of the tangent line. So it still gives you exactly what it's always given you. The difference is you're now parametric, so your function might look like really weird. You've seen them look kind of like this. It doesn't matter. If you calculate dy dx right here, it'll give you the slope of that line. All right, so it gives you the same information. The formula for it is you do the derivative of y with respect to t times the derivative of x with respect to t. It's super easy. You can see if you multiply by a reciprocal, if you did dy dt times, and then you flipped dt dx, these would cancel, and you can kind of see it like manipulation-wise equaling dy dx. So it's quite easy. The only thing kids sometimes do is they do it backwards because x is always given first, but dy goes on top. So just be careful that you don't go too fast. But if I were to graph this curve on my calculator, which I'm not going to do, if I want a function that gives me the slope of the tangent line anywhere on the curve, which would be called dy dx, I'd just do dy dt. So I'll take a derivative with respect to time over dx dt with respect to time, and then I'll plug in 3 for time. So it's actually very easy. I'm not going to spend a whole lot of time on this first derivative. But what is the derivative of y with respect to t? Grab the second one and it goes on top. What would that be? Hello? What's a Yeah, 3t squared, and since I'm doing it with respect to t, it's just like normal. So my top would be 3t squared, the bottom would be 2t. I'm just giving you an easy function. You cancel off a t on each one, and I'd get 3t over 2. That will give me the slope of the tangent line anywhere on the curve. I don't know what it looks like, but if I did, I'd know some information. When I plug in a 3, I know I get 9/2. Right? And that tells me that at that time, the same information a positive derivative has always told us. It means the function's doing what there? Increasing. It's not going down, it's going up. It's going up pretty steeply, and that's done. So easy first derivative. So now we'll go do a tricky one. If somebody could go graph this, because I haven't since last year, and I don't actually remember what the graph of that is, so do you want to take one for the team and graph that? Do it from t going to 0 to 2 pi. We'll just get one person. We don't all need to go graph since you all know how to do it. But let's talk about what she's going to set her calculator to go from. What's her x window going to go from, just to make it nice? -1 to 1, right? How about the y window? -1 to 1. That'd be the easiest way to set it. I'll have Sydney go hit graph, and we'll look at it. But meanwhile, while she's doing that, we're going to go find the rate that the y is changing as x changes. Slopes of the tangent lines at 3 different spots. It'll match up with our graph is what the reason I want her to do that. So let's do dy dx. First thing I do is dy dt. Nice and easy derivative, Luke, right? What's dy dt? So we go 2 cosine 2t, right? And dx dt is just cosine t. There's some important stuff coming with this. I'm just giving you an easy one right here to start you off, but there's some higher level questions coming up. So this would be my dy dx. Let's go do it at a couple places. First place, let's calculate our derivative. Let's do it at pi sixths. Good so far? Easy, right, Larkin? Just use a new formula and don't forget it. So we'd have 2 cosine pi thirds. When I plug in pi over 6, on the bottom I'd have cosine pi over 6. I chose this one to bring the unit circle back because it's been a while, right? Off-non, are you confident in what cosine pi over 3 is? It is. This is a half, so 2 times a half is 1. Are you confident, Chuckles, what's cosine pi sixths? Root 3 over 2, that's a complex fraction. We never leave it, right? So we'd have 2 over root 3, and that you're allowed to leave. It's better than 2 root 3 over 3, right? So that's done, easy peasy. You guys go do it at pi over 4. All right. I do. Once it's a bow tie. Okay. Looks like that kind of the bow tie pasta. We'll go put it on there, and I want to talk about what's happening at certain places on there. So you guys go do pi over 4. Meanwhile, I'm going to put the graph that popped up on the calculator. It kind of went bow tie-ish, like, is that kind of right, Sydney? What are we getting at pi over 4? What that means is on the graph, pi over 4 would be right about here, and you're finding that. Does that make sense? If it asks you some similar questions, if it says, where does the function have a horizontal tangent line? What do you think you find? Let's write that on here, actually. If it asks for where the function has a horizontal tangent line, what math do you think you do? The derivative equals 0, and now we can be even more specific. For the derivative to equal 0, the top has to be 0, and what's the top of your derivative? dy dt. Yeah, horizontal tangent. Now, there's a little glitch to it. dy dt equals 0, but dx dt does not. Right? Go plug in a pi over 2. Did it say 2 next? So now go do the third one. Go do dy dx at pi halves and watch what happens. And then I'm going to add another little disclaimer in here. When you do it at pi halves, what do you end up getting? 0 over 0. So we end up getting this. If I know you guys, I saw it, I was walking around. If you do this at pi halves, you end up with this. And I want you to know what this means for, it hasn't happened yet because you haven't been moving parametrically. You've just been moving along the x-axis and along the y-axis. So I'm going to have you get the detail. The math of this is easy. It's the details that are going to get you. So horizontal tangent line is when dy dt equals 0, but dx dt cannot. Yep. Isn't it? What? It's it's negative 2 over 0? Oh, sorry. That's actually going to tell me something else. That's going to tell me where there's a vertical tangent line. Vertical tangent line is the opposite. That would imply that dx dt, the denominator, equals 0, but dy dt does not. Where do they both equal 0? I'm actually not looking at, I think it's at pi, isn't it? Where do they both equal 0? dy dt and dx dt. Where do they both end up being 0? Because that would indicate this guy. Can you guys find the t at which that happens? You could do it on your calculator, but you'd have to end up getting 0 over 0, and I'm not quite sure where that happens. Anyway, whatever, we'll write that on here. Write this, if 0 over 0, this implies a cusp. So I want you to know the difference between these three. If you get a 0 for dy dt, it means it's not moving left or right. So let's go to another one. Second derivative. So first derivative is easy. The second derivative is weird. So you would think your gut reaction actually will not be correct for the formula. The proof of this, I've never seen one that I understand or can do or that's even done all the way. I can show it to you just by kind of brute force, but watch. So we know that when you, let's get out of parametrics for a second. What do you do when you take a second derivative, just on the right, just in general? What would I do to take a second derivative? I take the derivative of this, right? I take the derivative of y prime with respect to x. This would give me the second derivative. So using that analogy up here, if I want to take a second derivative, I'd replace y with y prime. Watch what you would get. You'd get the second derivative, and we always write it like this. If you forget y, it's because you're taking like that. You can see the two d's being squared and then the dx being, that's why the notation looks like that. I'm going to take that off of there though. If I replace that y with a y prime, I'd be doing the derivative with respect to t of the derivative. And you would think that would be your answer, but you actually still have this dx dt on the bottom. So it's a little goofy. And it's not what your gut would think. You'd think it'd just be the derivative of the first derivative. But you have this dx dt on the bottom. I want you to show it. I want to show it to you with the units on here. Are you ready? So I'm going to go in blue. You don't need to write it down. I'm just going to show you in blue. If I divide, wouldn't I multiply by a reciprocal? Watch. So I'll do the derivative with respect to t of dy dx, right, times dt dx, and watch what happens. Gone, gone. Do you see how I get d squared y, dx squared? This guy right here is what most kids forget, so put that on there. You do it as your gut would think, and then there's some extra dx dt in there that you would not think to do. So we're going to go down here, and we're going to go take a second. By the way, it still tells you what second derivatives always tell you. What do they tell you about the function? Concavity. Yep, so this still gives you concave up, concave down information. It just gives it to you for non-functions, but a second derivative right here parametrically will be negative because you're concave down over there. All right, let's go take this and follow the procedure. You're going to go with your gut. You're going to take the first derivative, right? So my first derivative would be, we already did it, right? So I'm going to say dy dx equals 3t squared over what? And I'm just doing easy ones just so you have it, over 2t, which is actually 3t over 2. This is where you change. You would think you'd just take the derivative again and have it be 3/2. Close. You take the derivative of that again, right? You're going to take the derivative of that first derivative as you would think you would do, but then what did I say you have to divide it by? Because you're going to want to say it's 3/2. What does the formula say you divide it by? Go ahead. dx dt. What is dx dt? 2t. So you're going to have to be a little bit careful that you don't just say first derivative, second derivative. You also have to divide it by that weird, I once, like a few years ago, we were trying to write a proof for it. We were trying to use the quotient rule and couldn't get it to go, and we Googled it. And there was a proof that started the same way, and then it went dot, dot, dot. So I was like, there's a kid named Jordan Hawk. Do you remember him? And it's years ago, but he was sitting right here, and we're like trying to do a proof, and I'm like, I'm stuck, and he was like, I'm stuck, and we went and Googled it, and the proof went dot, dot, like quit right where we quit. So the proof of why that dx dt on the bottom, I don't know where it comes from. I can see it when I work backwards, but not forward. Did you see me work backwards and I got it? So that needs to be there. Your answer would be 3/2 over 2t, or 3 over 4t. So be very careful with the yes. Yes. So be very careful with your second derivative that you put that dx dt on the bottom, because your gut will tell you not to. And guess what? College Board always puts it on there. without the dx dt. So make sure you don't forget about it. Go with your gut and then divide by dx dt. So let's go practice on a tricky one. This is actually just our unit circle, which is a parameterized equation. X is a function of t where t is an angle. Y is a function of t where t is an angle. Let's go find the second derivative. All right, are you ready? So dy dx, and again, I'm giving you easy ones just so you don't get caught up in the derivative, would be dy dt, and you don't need to write that if you don't want to, over dx dt. So you just take them, just make sure you grab the right one first. It's this guy. Its derivative, Chuckles, is cosine. So I'm going to have cosine t over negative sine t. And so if I was taking the AP test, actually, what would I circle? Negative cotangent. Yep. So negative cotangent t would give me the first derivative. The second derivative, this is where you have to be careful. The second derivative is the derivative of this one. So let's see if you can think that out. What's the derivative of tangent? Secant squared. What's the derivative of cotangent? Negative cosecant squared. So what's the derivative of negative cotangent? Cosecant squared. You should be able to think it out. A College Board won't put that on the AP test, but this is cosecant squared t. That would be sitting there. Or 1 over sine squared will be sitting there. That's not the answer. Because what did I say you have to remember to do? Divide by dx dt. Dx dt was negative sine t. You probably wouldn't see that either. It'd probably look like, it might look like that. It might look like that. Just know all versions of it, right? What else could it be? I'm putting all versions of it up here, but what else could it be, do you think? Negative cosecant cubed. You guys can go with the flow. So moral of the story, you take the derivative of your first derivative with respect to t, but then there's another dx dt on the bottom. So be a little bit careful with that. It's not what your gut would tell you. If you go evaluate them at pi force, it'll tell you the slope of the tangent line. So go do dy dx there, and it'll also tell you concavity. All right, so go plug in a pi force for both of those. My dy dx at pi force, slope of the tangent line, that's easy. What's the slope of the tangent line? I can see it just from right here. I do it right there instead of cotangent. I don't like cotangent when I'm actually doing the math. What would the slope of the tangent line be if it's cosine over negative sine at pi fourths? -1, and it looks like -1 when I drew it, didn't it? Looked good. By the way, your calculator does this. We'll go do it in a little bit on the next one. The second derivative there, I want you guys to do and clean it up all the way. I want you to do -1 over sine cubed pi force. Back to pre-calc a little bit here too. Can you get that in its cleanest form? If it's free response, you could leave it like that. If it's multiple choice, you're going to have to match it to its best form. I'm going to see if we can, and again, I haven't done it since last year, so I'm going to have to work it out to its best form as well. Go try it. Go. No. No, well, you have to know how to play for multiple choice. That's why I'm having you try. Again, if it's an FRQ, you are allowed to leave this even with the sign command in it. Or you could even just do root 2 over 2 cubed on the bottom and leave that. But if it's a multiple choice, a lot of times they take it all the way. Same with natural logs, by the way. It's a good time to talk about little details. All right. All right, Larkin, you think you got it? You want to talk me through it then? So I'm going to repeat, though, just in case you tuned out. FRQ, honestly, I'd hate it, but you should stop right there so you don't goof up. But multiple choice, that would never be there. What'd you do, Lark? That could be left FRQ. You would never see that for multiple choice, so keep going. Where did that come from? Almost. Root 2 cubed would be root 8, right? It'd be root 2 times root 2 times root 2, which is root 8 or 2 root 2, but let's go even. Suppose we leave the root 8 over what? 8. Again, also fair game for FRQ, but often that's not going to cut the mustard for multiple choice. So then I flip it. Still won't work for multiple choice, right? What's next, Chuck? Yep, fine. Negative 8 over 2 root 2 probably still won't cut it. I'm playing, right? Maybe I see that and I circle. You never know when they're going to stop for multiple choice. That's why with you guys, and I haven't even begun to discuss this in AB yet. And we're just getting answers and we're happy. Like, remember last year, we didn't discuss these details until way later. Maybe you see that and you circle it. Maybe, right? It depends. They make you stop whenever. But what would be the best one? Negative 2 root 2. How many of you got it all the way to that? I would call that the best form. Now, having said that, just because we do things globally in here, not just in the day, I want you to write what you think the best form of this might be. I get it on an FRQ and I leave it because I don't want to wreck it, right? But on a multiple choice, that's not going to sit there. It's got a very nice, yes, it gets better than that, right? I think I had one of these on your last test and some of you couldn't clean it up right. It had a natural log with some cleanup. So what's the best form of this guy right here? ln 9 to the 1/2, ln root 9, ln 3 is the friendly version of that one. Again, I'm going to repeat, Mitchell, if it's FRQ, what do you write? That or that. Don't mess with it. All right, next up. All right, 2 more. So now I have this curve, and this is what your worksheet looks like. It's going to ask you about slopes, which means dy dx as always, concavity, which means second derivatives. They're going to get a little more complicated. I started you off easy just because I wanted to get the new concept down, but I've got some curve where the x's are controlled by a third party, y's are controlled by a third party. I said curve, I didn't say function because they rarely are. And what I'm going to do is find the derivative again. What the derivative is going to allow me to do later is help me find the speed and stuff and the arc length and all that good stuff. So my dy dx would be dy dt over dx dt. So let's begin. Eli, I haven't picked on you for a while. What do you think the best way for me to take dy dt would be? I could do it in my head if you're smart. Yeah, pretend you're distributing the 1/2 in. That's always user-friendly. When one of the functions is a constant, dump it in. If they were both functions of t, I'd have to use product rule, right? But I'm thinking 1/2 t squared, I bring the 2 out front and I get a t, right? Minus t, so it just comes out to be t what? Minus 1. That's my dy dt. That tells me how y changes. Where's there a horizontal tangent line right now? At t equals 1, provided 1 doesn't make a 0 in the denominator, then I have a cusp. All right, so you get graphically. But what that means is that when t hits 1, I'm going to be horizontal tan line. On the bottom, I do dx dt. That's nice and easy, right, Annika? What's the derivative of root t? Yep, never leave complex fractions. They're too hard to work with. So I would write 2 root t times t minus 1. That's good enough for me to figure out the slope. Here's the problem, though. How do I figure out what to plug in for t? I'm going to let you mull that over. They did not tell me what t is. So just raise your hand when you know what's got to, there's a little, you got to kind of go with what they give you. They must have given you enough to figure out what t is. Pop up a hand when you know what's going in for t, because they didn't tell me at t, they told me where the point is. So you kind of have to use a little problem solving. I got 3 hands up. I need more than that. Sophie, how do you figure out at t equals what? Because it says at 2 comma 4, great. At 2 comma 4, great. But now I have a function of t, and I want to know at t equals what? I would do that one, because x is easier, and x is root t. It means that 2 is the square root of my t. Agreed? So what's my t? So if they don't give you the t, it's there, it's hiding. I'm going to give you a multiple choice one in a few minutes from a AP exam where that's not given, and kids usually bail because they're like, what's t? So it's actually a 4, right? So if I go plug that in, my slope numerically would be, I'm seeing a 12. You guys know you need to watch my arithmetic though. There's 12. Now, next step. That gave me the slope. I want you to do the second derivative, just because it's a little funky when you're doing parametrics. You already have first derivative. Get me a nice clean second derivative that you can plug a 4 into. And I'm going to wait. One more example and we shall quit. Tomorrow is no notes. I'll tell you what we're doing tomorrow once we're done with this. There's the actual formula if you were to Google it. Let you work. It actually ends up cleaning up pretty decent, I think. Yes. Yep, I know the answer is what you're going to get when you plug a 4 in there. And then I'm going to show you how to do it on your calculator, sort of. This cleans up to be a really nice linear expression of t, by the way. Anyone get a really, what do I mean by linear expression? T to what power? 1. Who else got that besides Chuckles? What'd you get, Luke? 2t minus 2? Mm-mm. Anyone else? What'd you get? Yeah, 6t minus 2. Let's see how we get that. If you might have an uglier version of it that you don't realize. For me to take the derivative of my first derivative, which is what I need to do, that's what this means. Take the derivative with respect to t of your first derivative, right? So I go over here. What do you think I would choose to do to take the derivative of my first derivative? Right here, what do you think my choice is going to be? I would distribute. I would not product rule that thing. It's if you product ruled it, it probably got really ugly. So I actually need to do the derivative with respect to t of, I'm going to product rule that, 2t to the 3 halves minus 2t to the 1 half. How many of you chose to go that route? All right. If not, I think it might have gotten really ugly. All right. Now watch me go take the derivative of it. Chuckles, you can go ahead and talk me through it. What'd you get on the top up here? What was this guy's derivative? Yes, he's going to bring it out front. 2's cancel. He gets 3t to the 1 half. So 3 root t, right? Minus 1 over root t or t to the negative 1 half. Doesn't really matter, right? There it is. If you left that as your answer, anyone leave that as their answer? Because if you did, what'd you forget? All over dx dt, which actually means multiply by the reciprocal. Is that what you did for your, that's what I would do. So now when you distribute this in, by the way, if you're sitting there with this, it's right, it's just ugly. 6 root t is 6t. And then when I dump this in here, I get minus 2. So I have a question for you. Are these easy or not? What do you think? It's easy with a twist, right? Watch your arithmetic, watch your trig, it's all over the place. So last up, this is the parametric one we graphed yesterday. Remember we graphed it on our calculator? Now we're going to ask some other questions. I want you to do part A right now. And then we'll do B and C together. And then I'm going to group you up for 5 minutes. You'll need your calculator, by the way, because you're going to be plugging 1 in. If you're in physics, make sure you get it back to radians. This means 1 radian, not 1 degree. I don't know what sine or cosine of 1 radian is. It's not on the unit circle, so By the way, run your work across. We'll do it. We'll do horizontal A, B, and C because vertically you have to squish it. Then I'm going to show, if you have your calculator out, I'll show you how, if this is calculator active, I would not have done it this way. But just for now. I'll steal an answer when you get it. What do we got? Negative 20.879. We are agreeing. Negative 20.879. It's almost going due north. It's super almost straight up and down. At t equals 1, it's almost going straight north. Do you agree with me? All right. So we should now, on your, those of you with the calculator, here's another way you could have done that. Are you ready? I'll give you a minute because today I'm not giving you a whole lot of homework to do. Go enter this in your parametric x1. Go enter this in parametric y1. Enter it as you see it. You don't need to see the graph to get it to do the first derivative. So if you enter them in, you don't even have to mess with the window or anything, I don't think. If you do second and then the trace, or if you go to the calc, there's a dy dx option. There's no second derivative option, but it'll actually do a numerical first derivative. Go give it a whirl. It just needs you to enter t equals 1 in. Go try it. If you go second calc, you've got something goofy with yours. My guess is you're not in radian mode. You got it? Yeah, so if you go second calc, just so you know, just in case it's FRQE, you can actually go in there. Larkin, when yours is moving that slow, here's another thing. I don't know if I told you this last year. If you're like, oh crap, I said it too slow, you don't have to wait for it to finish. Did you know that? You can hit the on button and it stops it. If you're like, hit the on and it stops the graph and you can go back and up your T step to like a 0.05 or. So if it goes too slow, don't wait. All right, do we got that to work? Next up. If I'm trying to, you guys are quiet, but you're focused. Rand, if I want to know where the curve is horizontal, that means has a horizontal tangent line, what am I concerned with? Where dy dt, is that what you said? But also, dx dt can't be. However, I can see by my graph that's not going to ever happen, because what did I say happens when they both equal 0? Do you remember? A cusp on the graph. Yeah. So what my calculus is going to give me is this guy, the next guy, the next guy. There's a whole bunch of places. So we need to go take dy dt, which I already found. 2 sine t has to equal 0. Sine t has to equal 0. Where's the first place that happens? 0, then pi, then 2 pi, then 3 pi, in particular n pi, right? Again, we didn't run this. It didn't give me a t restriction, so it's going to happen right away. And then it's at pi, 2 pi, 3 pi, 4 pi. Every time it's going to end up coming to the top and then going to the bottom. Next question. Who haven't I picked on today? Danny, how do I figure out where there's vertical tangent lines? Yes, dx dt equals 0, which means it's not moving on the horizontal, so only y is changing. That makes sense, doesn't it, with rates of change? X is not moving left or right. Its rate of change is 0, so y is going like this, creating a horizontal tangent line. But also, technically, you should keep this in mind, although College Board won't throw that at you. If you were in college, that would be an issue. So we have to go look at where our dx dt equals 0. What's dx dt? 1 minus. All right, are you ready? I want you guys to see if you can use your pre-calc. This is a pre-calc. Go see if you can use your pre-calc to figure out where that happens. And you can just go dot, dot, dot after you list about 4 of them so that it's clear there's a pattern. And then I have to tell you how to answer your questions. Because I was really sloppy on the last one, I'll tell you why. If it was me on an FRQ, I just got a point off. Pop up a hand when you've got the first place. Where's the first place that cosine t equals 1/2. First place. Pi thirds, it's getting the rest of them that some of you I still worry about. Working that unit circle. The first place cosine is 1/2 is at pi thirds. The next place is over here. Where is that? 10 pi sixths, also known at 5 pi 6 is over here. Actually, it's over here. Sorry. That's 7 pi 6. What's this guy? 5 pi thirds, right? And then this is 6 pi thirds, or 2 pi, and then 7 pi thirds again. And then you notice it went 4. The next one would be 11 pi thirds. But just so you can see a pattern, you can quit. Actually, though, I want you to read the question carefully and tell me why. If this was an FRQ, LaRue just lost a point, and she's trying to ace I'm trying to ace an AP test. I was just very sloppy in how I answered the question. Read the words carefully. What does it say? It doesn't say anything about, that's actually the issue. It says where, and what did I give? When, right? So it's when t equals 0, when t equals pi, when, how do I get the where? What do you think I have to do? I have to actually go give an ordered pair. So I would have to say 0, comma, I have to go put back to my original and put 0 in here. So it'd be 0, comma, 2 minus 2. So 0, 0 would be the first place. I can actually see it off my graph, comma. Same here for where you'd have to do pi thirds, comma, wherever that happened. So be careful with the where and the when. We are done. Yes? Yes. Yeah, so if it said when is there a horizontal tangent line? When t equals pi over 3. Where on the curve is it? X comma y. Exactly. So you'd have to take pi over 3 and put it into here and here. Here's what I want you to do. In your rows, I want you to answer these 4 and see if you've got the concepts down. So those 4